Okay, hi everybody, and welcome to today's meeting. Today we are going to have two guests that will talk about network programmability and orchestration. And the seminar will be given by Walter Cerroni and Davide Borsatti, who are both in the room. So Davide Borsatti is assistant professor in University of Bologna, and he works on programmable networks and SDN and NFV service function chaining. And Walter Cerroni is associate professor at University of Bologna. We have collaborated also in other papers, and we co-organized a workshop in Italy recently. And so I have the pleasure to invite both of them to present the Restart project, which is the Italian equivalent of the PEPR. And in particular, they will focus on network programmability and orchestration. But I now leave the floor to Walter. Just check that the mic is working.
Thank you, Leonardo. Can you hear me?
Yes.
I think it's okay. Okay, thanks again, Leonardo, and thank you for being here or online to this attend this seminar. I'd like to thank again Leonardo for inviting us to give this seminar, which was somehow related to a tutorial that we gave to a conference, the High Performance Switching and Routing Conference that was held in Pisa last summer, where Leonardo and I also organized a workshop. So Leonardo also asked me to contextualize this talk in the framework of the Restart program. The Restart program is basically the funding program that is based on the Next Generation EU funding from Europe, and is part of the National Recovery and Resilience Plan, which has been patronized by the Ministry of University and Research. So this is a funding program specifically targeted to telecommunications. And in fact, the Restart means research and innovation on future telecommunication systems and networks to make Italy smarter or more smart, whatever you want. The funding is more than 100 millions, which for Italy's standards, I think it's quite a large amount here. We're actually in the last year of this program, just started in January 2023. And the program is basically funding 32 different projects that are separated and split into large project and small focus projects. And initially, the partners that were part of the program were 26 core partners. But then we had a sort of cascade call system. We had a couple of calls in the past couple of years. So more partners could join the program. Now I'm not going to. This is just to let you know which are the partner, the core partner that started the program itself. Basically, you can find some of the major universities in Italy and also some of the major players like Telecom Italia, Vodafone, Wind Tre, Ericsson, and other players there, HPE and other players in Italy. I'm not going to go into the details of all the projects because there are so many, but I would like to show you what is the structure of the project, how it has been conceived to focus not only on research, which, as you can see, is of course the first mission of the program itself. But the research is not only outcome that we want to find. So there are other missions, as you can see. The program is funding laboratories, it's funding innovation and teaching transfer. So the possibility to get the results from our research and then transfer that knowledge to industry, for instance. Support to startups, education and training, PhD programs, and as well as all the communication and dissemination part. So the whole program has been conceived to not only do research and write papers, but also to try to really move forward innovation in the field, in the telecommunications field. And the organization is made by, it's a sort of hub and spoke architecture, where you have the central hub, which is the University of Tor Vergata, which is the leader of the project. And then you have many spokes in different university or research center that are focused on specific topics. Of course, telecommunications covers several topics. And as you can see, there are several spokes that are actually focusing on those topics. You go from pervasive and photonic technology, you go to integration of the network and services, wireless network technology, programmable networks, industrial networks and digital twins, and many other topics that you probably are familiar with. We are mostly focused on Spoke 4 and Spoke 5, especially the content of this talk is related to programmable networks, at least the part that I'm going to introduce. And then what Davide is going to present is more related also to the idea of having digital twins in industrial environments. In particular, for what concerns Spoke number 4, which is again focusing on network programmability, I'm part of this project, or we are part of this project, which is called Super, which is focusing again on programmability. And one of the results that was recently published from this project is a vision paper on what are considered morphable networks for cross-layer and cross-domain programmability. So this is the publication that recently appeared on the VTC magazine of the IEEE. It has a vision of this concept of a morphable network where you basically try to program the network not only horizontally or vertically, but try to combine both vertical and horizontal programmability. So across protocols and across different layers. I'm not going to spend too much time on this, but I give you the link if you want to learn more, if you want to know more about this super project. And another important aspect that is currently the focus of the activity in this project is to try to tackle what are called the grand challenges of the Restart program. So when you want to innovate the telecommunication sector nowadays, you need to, of course, deal with several important challenges. And these are the challenges, the grand challenges that have been defined by the program. And the activities currently of the last year of the project are focusing on try to tackle those grand challenges. And in particular, as I was saying, since we are involved in the network programmability part, one of these challenges is to make the network platform a platform for programming and running applications. So the idea of having our network infrastructure that is actually possible to program based on what is the service that we want to offer. So network programmability is the focus of this brief introduction that I want to give you before I leave the floor to Davide. You probably know already which are the main enablers for network programmability. So software-defined networking, network function virtualization, and all of them basically contribute to this programmatic approach to the way we manage resources and services and deploy services in the network. Now, if we take a little bit of a look back at some sort of retrospective look at what has brought us to the current idea of network programmability and where orchestration comes into play. Probably you know this paper. This is a survey that was made a few years ago, actually quite a few years ago, because it's more than 10 years that was published. But if you haven't never read that, I suggest you to do that, because it gives you quite a good view of how we reached the idea of having a programmable network, starting with the road to software-defined networking. Now, you can find several, let's say, enablers that, also from a historical perspective, brought to the current idea of what was at that time the idea of software-defined networking, like active network, the control plane and data plane separation. There are several initiatives that started since the mid-90s about the idea of having programmable networks and separating the control and the data plane. And then, of course, there is the network vectorization. Actually, what is interesting is that there is another paper that is a little bit more recent that is also trying to discuss the origin of the network programmability. And at the end, probably you know some of the names of the authors. And this is interesting because they actually mentioned the fact that probably the idea of programming the network dates back to the introduction of digitalization in the telephone network. So when you started moving from the analog telephone network into digital, you started doing something that we can actually consider programmable. So it's very also here it's very interesting if you want to read more about this. So this is another interesting paper that I suggest you to have a look at. Now, of course, I'm mentioning some works that the first one that I was mentioning is now quite outdated because there are still more than 10 years after that. So we need to cover that, of course, in order to understand where we are now. But there is another point that we need to consider better, and we need to focus more with respect to those papers. And the other perspective is computing, because nowadays, at least this is my opinion, we cannot talk about networking, especially programmable networks, if we don't take into account the evolution of computing and computing technology. So that's why this, timelines that are very beautiful that you can see in those papers must include also a timeline related to computing. Now, before we fill that empty timeline there, let's just recall what were the latest innovations after the introduction of SDN OpenFlow that dates back to a decade ago. Of course, we had the introduction of before on the actual programmability of the data plane and also other technologies that brought us, for instance, to have in network computing. So basically, the idea was to go from the OpenFlow perspective in programming a network, the software-defined networking, which basically was indeed an innovation. But if you think about it, when you program a switch using OpenFlow, you don't program the switch itself. You basically program the control plane because the intelligence is in the control plane. So this brought some limitations and some limited flexibility to the capability of the data plane itself. So that's why this idea of having match and action rules, when you can actually have hardware that is able to combine different layers of different pipeline, different phases of match action rules, you can actually program. You can introduce stateful packet processing, and you can really program the data plane. Using, for instance, domain-specific languages like before that allows you to do this with much more flexibility in the data plane itself. So this gave us the possibility to also move some computation inside the network data plane. And of course, this is not only possible inside the network nodes, the switches, but you can also take advantage of the smart NICs, the network interface card that you can program, that you can equip with programmable hardware, and then you can basically come up with solution of data plane programmability directly in the hardware at the hardware level. So basically, when we talk about programmable network nowadays, we have the choices to have a real, as I was saying, programmable data plane, where you can basically have switches that are programmable. You can have a server with smart NICs that are programmable, or you can also have some sort of converged architecture where you have the flexibility of having both systems. This really depends on what kind of infrastructure you have and what are the capability of your network, and if you want to work more on the server side or on the network itself. So now we can actually fill in the other timeline. So why we need to consider also the evolution in computing when we talk about networking? Because we need to consider the fact that virtualization is a key factor nowadays in networking, and virtualization was born quite some decades ago with the very first experiments on virtual machine, on virtual execution environments. Also, the first ideas of containers that started more than 25 years ago. And then from that, of course, there is the rise of cloud computing, which is another very important paradigm that is impacting the way we program networks nowadays. And of course, all the platforms, the software platforms that we use to manage virtualized environment, manage containers, to orchestrate containers like Kubernetes. And this is where basically the two paths, the two timelines actually becomes entangled. Because when we started talking about network functional virtualization, when we started talking about multi-access edge computing, and then the platforms to manage this kind of paradigms came out, like OpenSource MANO or ONAP or all the other NFV platforms. Basically, we are seeing the actual penetration between networking and computing. And also, this means that how can we virtualize network functions? So the idea basically is to apply the lesson learned from cloud computing into network. So we can have virtual network functions that are based on virtual machines with the whole virtualization of the whole stack, of the whole operating system, or we can have containerized network functions that are basically based on the isolation and the execution environment provided by container technology. Of course, when we virtualize something, we need to take into account that we need to cope with increasing workload. And then of course, the straightforward way to cope with increasing workload is to apply the scaling techniques that are used in cloud computing. Scaling out, meaning you replicate your network functions, or scaling up, meaning you make bigger functions with more resources. However, we must pay attention to the fact that network functions are different from cloud applications, because we have inherent problems related to packet processing. And in particular, the major bottleneck in virtualization is the fact that if you run a virtual network functions as a virtual machine or even as a container, and then you receive packet from the network interface, you need to move from the user space, from the kernel space to the user space and back. So these are the problems that basically make everything slower and so reduce the performance of virtualized environment. So that's why there are also, besides the data plane programmability hardware solution, we also have software solution that are able to solve these issues, like basically the kernel bypass. So you move directly the packets to the user space, to the processing in the virtualized network functions, or you can actually build some network functions at the kernel level, for instance, using eBPF, XDP, and other kernel level technologies like that. And of course, there are some recent activities, some recent initiatives that are building on this entangled, let's say, I would say, evolution between networking and computing. And of course, 5G and what will be the future 6G are heavily based on this kind of paradigms. So we have all these elements, all these blocks, programmable objects, server side or on the network, all these resources that we can actually program. But we have to factor in also the user, so whatever the user is actually requesting, and the service itself. Service that can be very complex, that will require composition of different elements that have several requirements in terms of performance and other aspects. And of course, we need to consider also the deployment level. So is this going to go inside a single data center? Are we going to take advantage of fog computing, of edge computing, so reducing latency? So this means that also the infrastructure becomes complex, and then we need to have something that solves the issues of deploying services over this heterogeneous infrastructure. So that's why we need an orchestrator. We need something that is able to collect all the, let's say, all the data that is coming from the infrastructure, is able to understand what is available in terms of resources, and is able to understand what kind of services must be deployed and how we can optimize the allocation of those services on the resources. So we are borrowing again from cloud computing. It's very important to understand, at least in my opinion, that orchestration is different from automation. Because you can have a very powerful automation tool, but the automation tool is for, simplify the management of a specific function. Orchestration means that we need to take advantage of automation, but we have to concentrate on what we call a workflow. So what is exactly we want to do, and what are the resources that we need to involve, and again, how we can provide the service on top of those resources. That can be hybrid, they can be of different nature. So that's why when we talk about network orchestration, we need to consider heterogeneous resources, network storage, compute resources across heterogeneous infrastructure. And even, that this is really challenging, even across different administrative domains, not only technological domains that are different, but also administrative domains. So this is the real challenge that we need to tackle, and this is where basically all the research that many people is doing on network orchestration is actually focusing. Well, basically that's another way to decouple things. So we have the services orchestration on top, we have the resources orchestration on the bottom, and then we need some sort of middle layer that is able to put together the two levels. So again, decoupling is, as usual, as it happens in several other situations, it's a key solution for solving this kind of problem. So coming back to Restart and back to Restart Grand Challenges, what I just overviewed in a very, very quick way is the idea that, of course, network orchestration is a key aspect to make the network platform a platform for programmable and running, programming and running applications. So the challenge that we need to consider includes not only the infrastructure itself, but also the orchestration. And I'm giving you just a couple of pointers for some of the works that we've been doing inside the Restart Super project on this topic. In particular, the first one is a way to define a scalable deep reinforcement learning approach to deploy services in a fog computing infrastructure. Here, the idea is to consider that fog computing could include nodes, computing nodes that are not always present. For instance, there can be devices that are temporarily connected to a network. So you need to understand how we can apply some sort of reinforcement learning approach that takes into account the heterogeneity and also the variability of the computing infrastructure. And the other paper is a paper related to data plane programmability, orchestrating data plane programmability functions for some specific use case on industrial security at the edge. So the idea here is to understand what kind of enhancement to the security inside the network, an industrial network, we can apply by implementing some security functions on data plane, on programmable data plane, programmable nodes using, for instance, P4. I'm not going to the details of these two papers. Again, I give you the pointer also because the people that are been doing most of the work are the students that are not here. But I would like to leave the floor to Davide, who is also involved, as I was saying, in another project within the same Restart program, which is the project that takes into account or is focusing on the challenge of exposed network infrastructure to services through digital twins. So the idea of having digital twins is in particular in some industrial scenarios. And Davide is going to present something, another paper, the results from another paper that we wrote together on this topic. So I think we can leave the question for later. But thank you for the attention. I will leave the floor to that.
Okay, so thanks, Walter, for the first part of the presentation. I will move to the other part that, as Walter was saying, is related to the grand challenge inside Restart on digital twins. And the idea of this work is trying to find a way to have a digital twin for Kubernetes environment. So this is an ongoing work with some collaborators from the University of Ferrara, Italy as well, and mainly from there. So what's the basic idea is we need a digital twin for Kubernetes environment that we could use to help the orchestrator understanding the actual action it might need to perform to orchestrate the resources needed on a Kubernetes cluster, for example, which is, as you might have seen from the countless presentation you've seen probably in the last couple of years, one of the most important technology for realizing containerized infrastructure. So we start with the design of the actual digital twin of Kubernetes. So we developed a sort of event-based simulator that tries to reenact exactly all the procedure that happens inside the Kubernetes cluster, meaning the scheduling of resources and the deployment of pods inside our infrastructure. I will not go through too much in the details on this part because it's, I think, were done mainly by the guy from Ferrara. Of course, you have the source code of kubetwin here, and you have the paper listed in the previous slide, and also on the last one. And so you can go through it. And I would like to focus also more on this other part, since also the timing is running fast. So after developing the digital twin, so the simulator for Kubernetes, we encountered a problem, and the problem was, okay, now we have a digital twin that more or less does the same things as a real Kubernetes cluster. But what we're interested into is not only Kubernetes itself, but also the services that run on top of it. Because most of the time when we use a digital twin, we want to know exactly how the application on top of it will perform, not only the cluster itself. So we started investigating how we can characterize the microservices that compose my application. So what you see here is a representation, generalized representation of what happens in a normal Kubernetes cluster in terms of traffic distribution among your different microservices. In this example, it's a very simple application composed of two microservices that are the circle that you see in here, 1 and 2, that have different numbers of replicas. For example, this is the first microservices, and this is the second one. You see it has lots of different replicas. And you have the standard load balancer, for example, done by the kubeproxy part component of kubetween that distributes more or less equally the incoming traffic towards the different replicas. And if we want to model it as a classical, again, queuing system, what you end up having is something like this, in which you have your incoming traffic request in here that goes through the load balancer, gets divided equally among the replicas of the microservices you are actually contacting. And so you end up having lots of different parallel queues before your actual replicas of your microservice. But since we are talking about microservices, this happens several times. As you can see in this figure, in 2, of course, you have a longer chain, you'll have the same behavior more times, in which each one of the microservices, after serving this request, they will send it to the next microservice in chain. And what's happened is basically the same thing, since the request will go through the load balancer of Kubernetes, that will redistribute again those requests on the second layer of microservices. So at the end of the day, what you end up having is a sort of multi-layer queuing system. Multi-layer since you have multiple layers of queue, and this is pretty difficult to treat with your normal traffic theory, since you have this nested queuing, which are difficult to treat analytically. So what you should need to understand the overall time that a request spend in this type of system, the usual thing you should do is do simulation. So for do simulation for this kind of problem, what we need to know is the behavior of this block in here, because we need to know the average service time, or in general the service time of those services here. So a naive approach, which was the one that we actually used at first, is okay, let's just measure the average service time of these microservices in a controlled way. For example, let's generate, I don't know, 5 requests per second or whatever, measure the average service time of a single replica, and use this data for all the other loads of our application. Well, we found out that this is a bit more complex, because we saw that the actual average service time, or in general, the service time of the microservices depends on lots of stuff. For example, here you see that going with increasing the traffic rate, so the amount of requests that comes into our system, which is on the x-axis, the average service time of the microservice decreases. So this means that there is a more deeper correlation between the actual arrival rate and the response time. Why this is important? Because if for example, we model our microservices with, I don't know, at 5 requests per second, and we want the digital twin to reenact exactly our system under a different type of load, for example, 30 requests per second, the result we would get from the simulator are actually far out with respect of the actual system. So in other words, the result that we would get from the digital twin are not exactly reliable. So we should not use it to, for example, dimension our system. Another correlation is also that one would say, okay, if you have multiple replicas, more or less you should have the same result. Well, there are fluctuations also in this case. For example, here you see the average processing time of the same microservices with different numbers of replicas. And so you see that what we expected is to have more or less the same values, but instead we have different ones. So again, this led us to think that we might need to take into account lots of other parameters, for example, the traffic rate and the number of replicas when we want to model the serving time of that particular microservice. So to do so, we realized a very simple machine learning model. Again, nothing heavy, so no large language model yet. In which is called MDN, which stands for Mixture Density Network, and in which the idea is to have our input, so the data that, for example, that we gather from the microservices running, and the parameters that were used to gain those processing time values. In other words, the arrival rate and the number of replicas, and use a very simple feed-forward neural network, which is the simplest neural network you might have, to try to, which the idea is that this network will try to extract this hidden correlation inside the measure that we got. So basically what I was showing in the previous slide, and use the output to feed a mixture model that will then try to give us the statistical distribution of the response time of that particular microservices with dependencies on the input parameter of the feed-forward neural network. So at the end of the day, what we would get in here is the statistical distribution of the response time of the microservice with the parameter that we set in here. So we might, for example, have the statistical distribution of the response time of the microservices with a lambda, so an arrival rate of 10 requests per second and 3 replicas, for example. And if we change this parameter, this output of this model will give us also the statistical distribution for example, unseen configuration. So to test it, we did, these are some details on how we actually realize this. These are the performance evaluation of the MDN model itself. So what you see here is the standardized Wasserstein distance between what was generated by the MDN model and unseen values from the system. So I don't know if you're more or less aware of what the Wasserstein distance is. If not, you might consider it as some sort of measure that indicates how far these two statistical distributions are. So the lower this Wasserstein distance is, the more closer these two statistical distributions are. Very, very briefly, if there are like people from statistics here, probably they will not be agreeing with me that much, but anyway, you just think about it in this way. And we compare it with the actual result that we got from the system. So in other words, we trained our MDN model. We get the statistical distribution of the processing time of all the microservices of the chain. We plug this statistical distribution in the Kubernetes digital twin, and we say, okay, give me the for example, the response time with in this unseen configuration, so a configuration that we haven't seen during training, and let's compare it with the actual result from the real system. And what we end up having is something with, in our opinion, pretty good. So the digital twin were able to reenact pretty closely the actual behavior of the application in the real system with a mean square error that is shown here. And so we were, let's say, happy with the result. And so we are continuing investigating this problem to try to see to extend this procedure to more complex applications. And also to what we're working on right now is trying to automate this process. And so because in this example here, all the data were gathered more or less manually from the logs of the microservice applications. And what we're trying to investigate if we, with some sort of distributed tracing or some sort of sidecar proxying, for example, with Istio, we could get the data live from the system and use it in a kind of online fashion to train the model at runtime with the microservice application itself. As we were discussing with Leonardo, this might have an impact on the actual measurement that we might get, since we are adding stuff to the system, so more computing power will probably be dedicated to the monitoring part. So this might also change. We might need to do some further fine-tuning on the model itself. But this is very, very briefly the work we were doing. I was carried off running out of time, but I think we are more or less aligned. Yeah, these are the publication if you want to check them. And of course, if you have any question here or maybe even later, you have all the contacts around the slide somewhere. So I think we can conclude in here, and I hope it was interesting. This talk was interesting to you. And if you have, again, any question, we are more than happy to answer them.
Thank you very much. So I will ask if the audience have questions. Otherwise, I have some.
Or two. Very basic question. So the first one is about the digital twin, and is there any interaction of the twin with the system? And if there is, I missed that.
You missed it because this is another ongoing work that we're doing. The idea is to plug the digital twin with a scheduler module that we want to work on. So the idea is that the scheduler of Kubernetes will take into account also the decision from this digital twin to assign the scores on the different nodes. So it will use this information to actually have a more smart schedule with respect to the normal, Kubernetes one. So this is another ongoing work that I forgot to mention.
And I have another question on the distribution, because I didn't get, so you train the network and then you get the distribution of service time condition to the population that you had at the input. And I didn't get how this allows you to make predictions on other states.
Because what you get at the output is a statistical distribution. And so the idea is that this statistical distribution will be sampled by the Kubernetes digital twin. So since an event-based simulator, it will say, okay, I have an incoming request. This incoming request will go inside this microservice. And what is the time that this request would spend inside this microservice is given by the sample from that statistical distribution.
It's not, so the X vector it doesn't mean number of replicas. The X vector that you give inside that conditions your distribution at the end. It's like 3 replicas of service 1, or it's something else?
Yeah,
Probably something else.
These are the parameters that were used to in this example. So, for example, here X contains the number of replicas and the average number of requests that your system gets. So here you have, let's say, a collection of what you have at the end of this MDN. You have a collection of statistical distribution. So you say, give me the statistical distribution that you have with 3 replicas and 10 requests per second, for example.
Oh, now I understand what you mean by mixture model.
Yeah.
That was the thing that I didn't get. So the mixture, it's the mixture of the possible configurations that you have, and I didn't get it looking at the picture. Thank you.
Thank you.
Thank you. I don't know if there are any questions also from the bridge. Otherwise.
Yes, can you hear me?
Yes, we can.
Okay. Yeah, thank you for the nice lecture. I was quite interested in seeing all these queuing network models.
Yep.
So could you say a few words on the I mean, whether this class of questions raises new queuing network theory questions, and if so, which ones?
The problem of multi-layered queuing system is something that was is already present in the literature.
Mm-hmm.
So there are already work that try to formalize this problem, but the problem is that usually you don't have an analytical way of solving this kind of queuing system, because as you might know from very basic queuing theory, the time that let's start from here. What is the time that a request spent in this type of system is the time spent on the queue and the time spent on the service itself. And this might be pretty easy to compute because you know this, you know the incoming request, you can compute the time that you spent on the queue. It's harder when you have multi-layer, since what is the time that a request spend in this type of system is the time it will spend on the queue, and the time it will spend in this other subsystem, which is composed by the actual service in your layer plus the overall time that you spent in this other sub-layer. And so this gets pretty complex pretty quickly, because if you have more than one layer, nested layer of queuing, then to compute this analytically is pretty complex. Also, you might see that here, for example, a request from this top queue might end up in another queue in here. And the same might happen for a request that gets served by the microservice in the bottom. So they both could go through the same microservices. So which is the arrival rate in here is pretty difficult to estimate.
Mm-hmm. So that probably strongly depends on the complexity of the load balancing step, I suppose, right? And
yeah,
so what would be typical mechanisms used in terms of routing based on this load balancing steps? What would be the typical framework used?
Yeah. Well, in Kubernetes, in your standard version, because Kubernetes is pretty modular, so you might install different modules that does different types of load balancing, but your normal load balancer will simply divide the traffic equally alongside the all replicas. So, for example, maybe you cannot see, but if I zoom in here, you see that your Lambda enters the load balancer that distributes this load in an equal way among the different replicas.
I see. But in that case, I mean, it's like random routing, right? Sort of, right? And then you might have, I mean, under natural assumption, a product form, even in this multi-layer case. Is it right, or?
I didn't get the last part, sorry.
No, I was wondering if the load balancing is just like a randomization, right?
Yeah.
Then this would be like a Jackson type network, or and if you would take exponential assumptions on the service times and Poisson arrivals, you might have product form in some cases. I mean, and therefore tractability.
Yeah, but I don't know if the assumption of, for example, post on arrival might still be valid in here, because the arrival rate in here depends on what happens in this other system, plus the randomization of this load balancer.
Right.
So I think you cannot really estimate exactly the Poisson distribution in here. So that's also another problem. And if you don't have, of course, this assumption, then how do you compute what's after that gets complex.
If I can add, I don't know if you can hear me. If I can add something. This is not a classical queuing network like the Jackson queuing network and so on. Because as Davide was saying, the service time of the first stage includes the sojourn time in the second stage. Because the microservices in the first stage is actually sending a request and is waiting for the reply from that request. So it's not like a packet network where you process the packet and then you move it forward, and then your service in the first stage is complete. So that's the real difficult approach that that characterizes this kind of models.
I see. Okay. Thank you. So then, actually, these service times are much more entangled. And okay, I see.
Yeah. That's why you need to do simulation to try if you want to know, for example, the sojourn time on the overall system. The literature in multi-layer queuing most of the time suggests you to do simulation. So you do a simulator that simulates this type of system, and from that you can estimate the sojourn time.
And so this interaction, can they be represented like a feedback with some information coming back from the second stage to the first, or things like that? Does it make sense? Or
this might happen as well, yeah.
Okay.
Because it depends a lot on the actual chaining that you have on your microservices architecture. Because some of these you might come back, for example, to different microservices more than one time. Yeah.
Okay. Thanks a lot.
Thank you.
Thank you very much. I had some more questions, but we need to give the floor to Ashutosh for next talk. So the talk is on another link. You can check the link in the calendar. So we will switch off this bridge, this Zoom bridge, and we will connect to the other bridge. So let's thank again the speakers and
thank you for your attention, for being here.
Thank you.
So